So we're starting with a mixing problem today, where we've got a tank or a vat, if you prefer. Vat, a tank, okay? And I typically make my vats look like this. They probably never look like that in real life. And I'm imagining, well, this tank has some pure water in it to start with, and I'm making my water blue, in spite of the fact that my 8th grade painting teacher asked me the color of water. And I'm like, in front of the whole class, by the way, blue? And he's like, no, it's clear. In front of the whole class, because he didn't like how blue I was making my water in my painting. And I'm like, yeah, but you asked me for a color. Anyway, so I'm making my water blue. And, you know, it comes from reflecting the sky, but okay, whatever. And so then we've got water coming in and water going out. We got an intake and we got an outtake. Excuse me. This is pure H2O, no salt in it at T equals 0. And how much water is in the tank? Should we use liters or should we use gallons? Let's use gallons for fun because, you know, the rest of the world used liters. Say 10 gallons to start with at time 0, but then salt water is coming into the tank at a certain rate. Oh, how about 6 gallons per minute? And a certain concentration of salt, maybe a number of pounds per gallon, or is that too many? Maybe it should be ounces. Okay, it's a lot of salt, say 2 pounds per gallon. That would be very salty water, okay? Coming into this tank, and we assume there's a green fan in here mixing up the water really well. It probably shouldn't be above the water level. That looks like a 4-leaf clover. Anyway, it's spinning, mixing up the salt water really well so that we can get away with the assumption that the salt is instantaneously mixed. Right? That wouldn't happen, of course. There's spatial effects. The salt needs to dissipate through the water. But we're going to assume instantaneous mixing. That is supposed to be a fan, a blade spinning, mixing up the water. It should be under the water, but it helps to see it better if I draw it above the water. And not only is that happening, but water's also coming out the bottom at another flow rate. Oh, let's say 4 gallons per minute. And another concentration, but what is the concentration? It's pure H2O at the start, no salt. But this salt water coming in does have salt in it, so there starts to build up salt, but it's also leaving the tank at a certain rate. That's the flow rate of fluid, salt water, but what is the concentration? Let's let S be the amount of salt in the tank. And we better use consistent units here. That would be in gallons then. T will be time. It would make sense to use the same units as before. That would be in minutes. Might be. Say, is salt in gallons? Yeah, thank you. Pounds. And the volume of water, of salt water, is going to go up over time. And, you know, even though there's a lot of salt there, 2 pounds per gallon, it doesn't really take up much volume. Or, you know, salt is granules, and there can be a fair amount of salt essentially taking up no volume. So V is going to be the volume of, we'll call it salt water. Maybe it'd be better to call it saline solution. Anyway, the amount of the concentration of salt is not constant. I hope it's pretty clear leaving the tank. It starts out essentially at 0 because it's pure water to begin with, but then more and more salt gets in there and instantaneously mixed. The concentration is getting higher and higher. It's not a constant. It would be S over V pounds per gallon. Yes, the volume is in gallons. And these are both functions of T. So the ratio is also a function of T, though I'm not specifying that in the notation. All right, so that's the basic model, physical model that you imagine in your mind. We're setting this up. We now want to come up with a differential equation that is supposed to model the amount of salt in the tank over time. And the basic physical principle here is that the rate of change of the amount of salt with respect to time should be rate in minus rate out. Basic intuitive principle. The units for the derivative would be units of the amount of salt, pounds per unit time. This would be in pounds per minute. And therefore, both of these rates would need to be in pounds per minute. For the rate in, how do you take those quantities and convert them to pounds per minute? Multiply. Then the gallons will cancel. You've got the concentration, 2 pounds of salt per gallon. It's a constant concentration, times the flow rate, 6 gallons per minute. The gallons cancel, giving you 12 pounds per minute. That is a kind of like a flow rate of salt, even though salt by itself can't literally flow. That's how fast the salt is coming in. For the rate out, we need to use this flow rate, 4 gallons per minute, times this concentration. S over V pounds per gallon times 4 gallons per minute. Once again, the gallons cancel, leaving you with pounds per minute. Simplify, 2 times 6 is 12, minus 4S. We could figure out what the volume is, couldn't we? We could pretty easily figure out how the volume of fluid depends on time. It starts out at 10 gallons and is going up by what? 6 minus 4, 2 gallons per minute, right? I didn't write that down before, but that certainly is true. This V is going to be a function of T. I could call it V of T if I like. It's going to start out at 10 gallons and go up by 6 minus 4 gallons per minute. So it's a linear function of T, 10 plus 2T. Moreover, if I assume this vat is finite, which that's probably good to assume, and it has a capacity of, say, oh, I don't know, 100 gallons, 100-gallon capacity, then since the fluid starts out at 10 gallons, it's got 90 gallons to go before it fills. It's filling at a rate of 2 gallons per minute, so it's going to take 45 minutes to fill, right? 90 divided by 2. I'd be assuming all this is true for T between 0 and 45. That would be the domain of T values for which this model would be valid. And yeah, I can take this 10 plus 2T and bring it down here, like that. The equality between ds dt and this thing is now a differential equation, a first-order differential equation. It is also an initial value problem because it's pure H2O at the start. S of 0 equals 0. That's our IVP that we would like to solve. All right, so let's go ahead and solve it, get a little bit more practice with, in this case, it's best to use integrating factors. We will also go ahead, make the slope field, draw a solution in there. Then we'll move on to numerical methods. We'll talk about quickly applying Euler's method, talk about errors with Euler's method in this case. We'll be able to compute the errors because we have the exact solution. Then we'll talk about a second order Taylor method, which is discussed in section 5.3, and its errors, and see how much better it does. And then As we have time left at the end of the class, then we'll start trying to dive into the theory a little bit, try to understand what's going on in the reading, the hard part of the reading, okay? So a little more practice with integrating factors. You should be able to use both separation of variables and integrating factors on the take-home final exam. Should also be able to do the undetermined coefficients. I think we only did one example in class. I shared a video with another example. Maybe I'll share a video with another example as well. This is my right-hand side function, my f of ts. ds dt equals that is written in the standard form to which to apply Euler's method. But if I want to use integrating factors, it's better to bring this part over to the right side by adding 4s over 10 plus 2t to both sides. And I'm going to write it as 4 over 10 plus 2t times s, bring it to the left side by adding it to both sides, equals 12. That's now in the form to which we can use integrating factor by taking that coefficient of the dependent variable, in this case s, before this point it's been y, and saying the integrating factor, typically called mu, but it has nothing to do with means, is e to the integral of whatever that is. In this case, it's 4 over 10 plus 4t. And when we do that integral, we don't need to bother with a plus c. Taking c to be 0 is the most common thing, and it's good enough. Integrate something like that, you are going to get a natural log. I hope it's pretty clear thinking about that in your mind. But it's natural log of 10 plus 4t. Is that going to be the right integral? Well, fortunately, it is. Is there a question? I make a mistake. 2t, thank you. Thank you for catching my mistakes. 2t. Okay, that makes it a little trickier. It'll involve a natural log of 10 plus 2t, but that's not correct because we wouldn't get the 4. We have to multiply that by 2 to get the right antiderivative. Differentiate this in your head. You get 2 over 10 plus 2t, and then the chain rule will give an extra factor of 2. 2 times 2 is 4. Yeah, plus c, you can take the c to be 0. That's not such a nice looking integrating factor, but it's actually simpler than it looks because you can use a property of logs to bring the 2 out in front into the power there, and then the e and the natural log are inverse functions, so your integrating factor becomes 10 plus 2t quantity squared, which we could expand out, but it's probably better not to bother. It's called an integrating factor because, first of all, you now take this and you multiply both sides of the differential equation by it, so it becomes a factor on both sides. And we can, when multiplying it by this term, go ahead and simplify, do a little cancellation, and get 10 plus 2t to the first power. If you do it to the left, don't forget to do it to the right. The most common mistake people make in using integrating factors is to forget to multiply it on the right as well. So it became a factor of both sides of the differential equation. And the reason it's a good idea to do this is that if you have correctly computed your integrating factor, the left-hand side of this differential equation will be easy to integrate because it is the same as what you would get by differentiating the integrating factor times the unknown solution s. Why? Think about using the product rule here. S does depend on t here, by the way. It's important to realize that. I'm not being explicit about that in my notation, but s is the unknown function of time that I'm trying to solve for. So when I differentiate this, I need the product rule. That's the first function times the derivative of the second, plus this is the second function, s. That thing is the derivative of the first. Yeah, if you differentiate this, you'd bring the 2 down in the front, make it a 1. You get an extra factor of 2 from the chain rule as well. 2 times 2 is 4. You would get this. And again, I'm not bothering to multiply this out. It's better maybe even not to. Being the derivative of this, it's easy to integrate. Now you integrate both sides. Integrate. You don't even have to bother writing an integral sign on the left because the integral of a derivative is the original function. The integral and the derivative cancel, so to speak. And once again, on the left side, you could multiply it out, but I think it's perhaps better not to. Maybe, maybe not. Integrate that as is, you'll get a 10 plus 2t to the third power divided by 3, and that's probably not quite right. We do need a plus c here, because you got to think about accounting for the chain rule. I mean, if I was going to be extra careful, I'd do a substitution, like w equals 10 plus 2t. Let's see, 12 divided by 3, that's 4. If I bring that 3 down, 4 times 3 is 12, but I get an extra factor of 2 from the chain rule, getting 24. To make it a 12, I think I need to divide by 2 as well. I know I said that kind of quick. I believe you can check it. Yes, it simplifies to 6 over 12 over 2 over 6. 6 over 3 is 2. 10 plus 2t to the third power plus c. And if you still don't quite believe it, check it again. Bring that 3 down. We're differentiating in our minds here. 2 times 3 is 6. 10 plus 2t squared times 2. 6 times 2 is 12. Still not done? I now have an algebra equation to solve for the unknown function s. I got to divide both sides by 10 plus 2t squared of all things. Okay, so it looks like a general solution is s equals divide both sides by 10 plus 2t squared. You're going to get cancellation with the 10 plus 2t cubed. The 2 will stay where it is. You'll have 2 times 10 plus 2t, and that is, of course, simple enough to multiply the 2 through. And then the c does need to get divided by 10 plus 2t squared as well. Yes, this does equal 20 plus 4t, and that maybe is worth doing. And that is a general solution. Not done, though. We also have an initial value. It's an initial value problem. S of 0 is 0. 0 equals S of 0 equals, plug in t equals 0, get 20 plus 0 plus c over 10 plus 0 squared. 20 plus c over 100 is 0. Excuse me. So c over 100 looks to be negative 20, and it looks like, if I've not made a mistake, that c is negative 2000. So if I have not made a mistake, it's entirely possible that I have. The solution function, I'll go ahead and use the phi notation now. S equals phi of t. Maybe even emphasize the initial condition is 0. That's the initial condition. Not that you have to put that there, but it is consistent with the notation I've used in the past. Looks to be 20 plus 4t minus 2000 over 10 plus 2t squared. And then we could use this to figure out the amount of salt in the tank after 45 minutes. What's S at time 45, which, to use better notation, would be phi sub 0 of 45. That's abusive notation, but we're okay with it. Plug in t equals 45, get 20 plus 4 times 45. 4 times 45 is 180, minus 2000 over 2 times 45 is 90, plus 10 is 100. 100 squared, 200 minus 2000 over 10,000. I can even do this in my head. It looks like 200 minus 0.2, 198.8 pounds of salt. If I've not made a mistake. Does that make sense? Well, okay, well, if all the water in the vat had the same concentration as the water coming in, 2 pounds per gallon, and it's full 100 gallons, the amount of salt would be 100 times 2, 200 pounds. Almost there. Not quite. Started off with pure water to begin with, but so much salt is coming in that it practically fills to the same concentration by the end. The ending concentration would be 198.8 pounds divided by 100 gallons, 1.988 pounds per gallon, if you were after the ending concentration. Almost up to 2 pounds per gallon. Okay. So, you know, this might seem like a silly application, you know, who would do this with salt water, but I mean, engineers in industrial chemical applications do need to think about mixing chemicals. So it's sort of like practice for such a problem. Though they need to think about spatial effects because if they want to be completely accurate, because it's not instantaneously mixed. But it does simplify things if you don't have to think about spatial effects. Because when you think about spatial effects, you have to think about partial differential equations. And we want to avoid thinking about partial differential equations when we're trying to understand ordinary differential equations. All right, let's now use technology to confirm what we've done here, first of all. So I'm going to go ahead and define my right-hand side function first. That was the original right-hand side function. 12 minus 4s over 10 plus 2t, right? That was the right-hand side of the first order equation. The STT equals that. So that's my right-hand side function, to which I could, for example, use this even still to use dsolve value to check my answer. Dsolve or dsolve value. I prefer dsolve value, just getting a simple form for the answer. My dependent variable I'm calling s now, though, so I'll use s prime of t. Don't forget to use double equal signs. If I've defined my right-hand side function, I don't actually have to type it in as I've written it. I can use the f function here, but replace s with s of t, like that. And then s of 0 equals 0, comma s of t, comma t. This should be syntax that will give us the unique solution of the IVP. It may not look the same as what we wrote by hand, but let's see how it looks. Okay, so there's how Mathematica writes the answer. Is that the same as what we got? It should be, if I didn't make a mistake. So we got this thing. So to compare our answer with Mathematica's, it looks like we would need to add the fractions. Let's try it here in Mathematica with, well, we might need to use, well, let's see what Mathematica does with our answer here. Okay, it does nothing with it. How about if I do together? Yeah, that works. Notice, maybe, I don't know if you've noticed this, but sometimes I put commands at the end with // That's called postfix operators, but I can also do it at the beginning as long as I put it in square brackets. 2 ways to apply functions. And you see they are the same thing. So we got the right answer. Happy about that. Let's go ahead and define that to be my solution function. I'll use my form of it. For extra emphasis, to check that this solves the differential equation, that would be good to emphasize here. What does that mean we can do with this function? It means if we plug it into the left-hand side of the differential equation, compute phi prime of t, which is the same as the STT, that's the left-hand side, get whatever we get. We should get the same thing as if we were plugging into the right-hand side of the differential equation. In other words, replace s with phi of t and simplify. This would be a way to check that we get the same thing. Do we get the same thing? Mathematica, what is phi prime of t? There it is. Mathematica. If I replace s with phi of t in the differential equation, do I get the same thing? At least if it gets togethered. Or maybe, no, okay. Do this one together as well. Yeah, the derivative and the right-hand side do simplify to the same thing. You could check that by hand. It does solve the differential equation. It's important to realize that's what you would need to check. That when you plug the function into both sides of the differential equation as functions of t, replace s in both spots with the function, that it simplifies to the same function of t in the end. Coming back to doing more technology, let's also make the slope field and draw the solution in the slope field. So let's see, let's do a show to combine graphics, vector plot to make the slope field. And with slope fields, inside a list, you first put a 1, then a comma, then the right-hand side function. T goes from 0 to 45 would make sense, since this vat fills up by 45 minutes. And S 0 to, say, 200 makes sense, right? Since it gets up close to 200 by the end. I mean, if you didn't know that, you'd have to guess it. I mean, it's actually not too hard to guess that might happen, since the concentration is 2 pounds per gallon going in. And what is it? Vector style, arrowhead 0. Then we also want to plot the solution function in there, the phi of t. He goes from 0 to 45, make it nice and thick. There we go. For most of the time, it's practically a straight line there, which makes sense. Once enough salt water has come in, the concentration of salt in the tank is pretty quickly almost up to 2 pounds per gallon. It doesn't get up close to 200 gallons until by the end, but the concentration is close to 2. If you draw a line in here with a slope of 2, it gets pretty close to that line pretty rapidly. Does that make sense? The concentration pretty rapidly gets close to 2 pounds per gallon, even after only 5 to 10 minutes have gone by. And the amount of fluid is up to 20, 30 gallons. Okay. There are other solutions of the differential equation, but they don't satisfy the initial value problem. Though the same differential equation could be relevant if the initial amount of salt were higher than 0. If we go back to our initial value problem, same differential equation, but change the initial condition to something positive. It'd be the same differential equation with the same general solution, but the C would be something different. It would still be the same slope field. And interesting to think about there is if the amount of salt is high enough to begin with, the solution actually goes down at first. The amount of salt goes down because if the initial amount of salt is high enough, the concentration of salt in the tank is actually higher than 2 pounds per gallon. Then more salt would be going out of the tank right away than going in. So the solution would actually decrease before it increases. In the end, though, the amount would approach getting close to the same 200, at least if the initial condition was not extremely high. All right, now let's use Euler's method. I won't bother writing it out by hand today, though in a few minutes we'll talk about a second order Taylor method, and we will write that by hand. Well, maybe for the sake of comparison, we should write it by hand. So again, Euler's method, For your generic initial value problem, I'm going to write it with a y here. dy dt equals f of ty. And the way the book writes, the initial condition is y of a equals alpha. I often write y of t naught equals y naught. Is that it's a recursive equation. It's sometimes called the difference equation. Generating a bunch of numbers labeled with w in this book. W sub 0 is the value of alpha. You could call it y naught if you prefer. And w sub I plus 1, the new value of w, is the old value of w plus some change in w. And the change in w is given by the value of f in the slope field at ti comma wi times h, where it's understood here that h is b minus a over n. Your entire interval that you're trying to approximate this solution over is the interval from a to b with n steps. H then is the step size. It's also understood here that ti is a plus I times h. This is just like the setup you use with estimating integrals as well. But this is the essence of the method right there. And this expression here is often called the difference equation. It's really function iteration, though more complicated than we did back in chapter 2. But it can still be implemented with nest list in Mathematica. To do so, though, however, in a nice way that also gives you t-coordinates, it's good to create a new function. I tend to call it EM for lack of a better thing to call it, standing for Euler method. It's got a two-dimensional input and a two-dimensional output. For the first coordinate or component, it's the t value, and the second one is the w value. And the w values approximate the y values for solutions. You want a two-dimensional output as well. The t just keeps getting updated by h. So what might be also good here is to say what the value of h is over here. I'll use h equal to 0.1 and see how it does. I could put the h there then. It's just one way to do it in Mathematica here. There are other ways. And then I could do update the w value by doing w plus the change in w. Notice you don't have to bother with subscripts here because nest list effectively is doing the subscripting by iterating this function. So you don't have to bother typing in this with subscripts. W plus f of tw times h. I could plug in h equals 0.1 in those two spots, but by putting it over here and having it as h over here and here, that would allow me to change h if I wanted to. What we're going to get for output when we apply nest list is a list of points effectively. We are iterating EM based on the initial condition 0, 0. And if we want to get out to time 45, when h is 0.1, we better do 450 steps. 45 divided by h. I don't know if it'll like it. If h is in there as a decimal, I don't know if it'll like this. Let's see what happens. Okay, I think yeah. There we go. It'll like that better. I could convert h to, if I did h as 1/10 instead of 0.1, then I could do 45 divided by h. It's the way it treats it, but then it makes fractions for outputs. There we go. And what is it predicting for the amount of salt in the tank by time 45? 199.8. when the true answer was 198.8. So this is an overestimate. This is doing worse than I was expecting. Did we get, I hope I didn't make a mistake when I computed B of 45. Oh, I guess I must have made a mistake. Oh yeah, way back when I wrote down that, I made an arithmetic mistake. 199.8. Sorry about that. I made a mistake. Okay. Arithmetic mistake. Okay, no, so it is doing well. Very close to 199.8 there. Just a little bit too high. It's off by 0.011. In fact, we could use this to now figure out the errors. We could find out a list of errors, in fact, even. Let's give this a name. Let's call it let's make H bigger just so we have fewer data points. Let's use H equals 1. It'll probably still do pretty well. Yeah, that's still doing pretty well. Let's give this list a name. We'll call it EM data. There's EM data. We could also do exact data. Generate a table of values using the actual solution function, t comma phi of t, t going from 0 to 45 in steps of 1, and we probably want numerical approximations here. And then we could also take both EM data and exact data and get error data. And I think we could, we probably need to do something like this here. I was thinking maybe we could do exact data minus error data, but I think that's a EM data. But I think that's a problem because it's two-dimensional data, and subtracting the first coordinates, it's going to give you a bunch of zeros. So that's not so great. With the second coordinates, it's good. So I think we need to do something different there. Maybe something like this. Exact data. Oh, how's the syntax go? I comma 2 maybe. And this is a little funny because, so this is generating lists, and I have to start I at 1 here because that's going to correspond to the first entry in each list. T would be 0 and I is 1. Then I is 2 corresponding to T equals 1. Ultimately, I have to go up to I equals 46 corresponding to T equals 45. There's 46 points in the data. The 2 here corresponds to the second coordinate, so to speak, in each one of these. I think this will work. Yeah, these i's keep going from, I guess I need to do I minus 1. The i's are now going from 0 to 45, and these errors, are they correct? For example, with T equals 45, the exact value is 199.8, and the approximation is 199.898. 199.8 minus 190, what was it? 199.898. Yeah, effectively corresponding to that error right there. So these are the errors, and something interesting happens with this example is that it gets more accurate as it goes. Why is that happening? These errors are getting closer and closer to 0. I think it's because the graph's getting straighter and straighter. And that slanted asymptote for the solution, it's not an equilibrium solution, but it's a slanted non-equilibrium solution that's other solutions approach. It's stable in a sense. And so you would expect, because of that, the slope feels very well behaved. And so you would expect, because of that the errors are probably going to get smaller, generally speaking. I mean, they're pretty bad at first, at least if H is 1. These are pretty bad errors at first. More typically, if you use H equal to like 0.1, they'd be better, closer to 0.